Okay, so apparently I'm gonna have to record each tab individually because technology is not on my side tonight, and I just don't have the energy to fix it. So I'm just gonna splice all these together and it'll be fine. So we're gonna go over this key real quick. Let me move this out of the way. So this is the half-life practice from last class. So you guys remember you did the circle and you cut it and you cut it again and you cut it again, talking about how much radioactive material would decay and stabilize versus how much would still be left over. So you did have some practice problems to go with that, and that was this. So what is meant by half-life? That was kind of in the notes that we went over. It's just how much time it takes for half of the radioactive material to stabilize. So you have decayed. Decaying is the same as saying that it has stabilized. So number 2 is 3 parts. Okay, so it says if you have 100 grams of a radioactive isotope with a half-life of 10 years, how much of the isotope will you have left after 10 years? Well, it's pretty straightforward on that, right? So if you have one half-life is equal to 10 years, you have only degraded 50%. Okay, so you'd have 100 grams because that's what you're starting with. It tells you right here. You're gonna have 100 grams times 1/2 is gonna give you 50 grams. So how much of the isotope we have left after 20 years? Same idea. Okay, so if you know that there's 20 years, you're going to divide that by how long one half-life is. So if you have 20 years divided by 10 years, that means 2 half-lives have passed. You're going to take your starting amount of 100, multiply it by half times 1/2, and it gives you 25 grams. C is just saying how many half-lives will occur in 40 years. So again, 40 years divided by how long the half-life is gives you 4 half-lives. On number 3, this is when they started to get a little bit more complicated. So the half-life of plutonium-239 is 24,300 years. If a nuclear bomb released 8 kilograms of this isotope, how many years would pass before the amount is reduced to 1 kilogram? So you first need to figure out how many half-lives have actually passed. So if you have only 1 kilogram left and you started with 8, you can divide that. So we have 1 divided by 8 tells you that you only have 12.5% remaining. So you can go back in, and that's what this little picture is that I put up here. Just like with those circles you guys cut out last class, one half-life would remove 50%, another half-life would remove an additional 25%, and a third half-life would remove an additional 12.5%, which would leave you with this 12.5% pie piece. So if you're looking at this, it's just going to be 1 half-life, 2 half-lives, 3 half-lives. Then you have 12.5% remaining. So you know that that's going to be 3 half-lives to get to this point of 1 kilogram. Now you have to go back in and figure out how many years would have passed before, before that happens. So if you have 3 half-lives times the amount of time that your half-life is, which in this case is 24,300 years, you're going to end up with 72,900 years is how long it's going to take before that plutonium degrades all the way down to 1 kilogram. Number 4, kind of the same idea. Okay, so you have the half-life of radon-222, it's 3.8 days. How much of a 100-gram sample is left after 15.2 days? So you have to figure out how many half-lives have actually passed in that time frame. So you know that 15.2 days has passed. 1 half-life is 3.8 days. So you're going to take 15.2 divided by 3.8. It's going to tell you that you have had 4 half-lives pass. Now you can go in and multiply the starting amount, which in this case is 100 grams, by half, by how many half-lives you have. So here we're just saying 100 times 0.5, 0.5, 0.5, 0.5. So you have 4 half-lives, which is going to tell you that your remaining amount of radioactive material will be 6.25 grams. So keep in mind that the sample is not going away. Okay, so if you start with 100 grams, you still have 100 grams when you're done. The only difference is that now, in this case, only 6.25 grams is radioactive after 15 days, where in the beginning, all of it was radioactive. 5 is done the same way. So you divide, figure out your half-lives, multiply your starting amount. So you should have ended up with 8.75 milligrams on that one. It's not grams. 6, let's see. This one was a little tricky because you were kind of working backwards on it. So for this one, it gives you the half-life is 5.26 years. You're saying if 50 grams are left after a period of time has passed, so after 3 half-lives have passed, I now have 50 grams of radioactive material. How many grams were radioactive in my original sample? So the only difference here is that instead of multiplying by each half-life to go from your original to the final, since you're going from the final back to the original, you're going to be dividing by each half-life. So we figured out there's 3 half-lives. So we're going to have 50 divided by 0.5, divided by 0.5, divided by 0.5. It gives you 400 grams. 7 is done the same way. Okay, so you figure out how many half-lives have passed, then you're going to divide that by each half-life. Number 8 is the last one here. So this one says we have 100 grams of gold 198 decays to 6.25 grams in 10.8 days. What is the half-life? So if we have 6.25 grams out of 100 grams to start, would have been 6.25%. Okay, so you can figure out your percentage, figure out how many half-lives that is. So I went back to the pie pieces here. So we know that if 1 half-life passes, you have 50% remaining. 2 half-lives pass, you have 25% remaining. 3 half-lives pass, you have 12.5% remaining. And then 4 half-lives have passed to give you 6.25%. So at 6.25% remaining, you have 4 half-lives that have passed. Okay, so if you have 10.8 days and 4 half-lives have passed in 10.8 days, you'll just take 10.8 divided by 4. So it tells you that each half-life for this substance is going to be 2.7 days.